All right, my friends. So we're going to be talking about kinetics. Yesterday I had hinted at the idea of a rate law. We'll spend most of our chapter over the next week or so talking about rate laws. A rate law is a mathematical expression that describes how the concentration of a reaction affects its speed, the reaction speed. So we're looking at rate. The whole chapter is about rate. What is rate? Justin?
How fast something happens.
Okay. And how would you describe fast?
Like the speed at which it happens.
And how would you describe speed?
Velocity as in velocity.
Okay. If I didn't know anything about speed, what would you say of velocity?
How long it takes for it to finish.
Okay. How long it takes for it to finish? You could apply that idea to a car moving, a bike, a person running, a reaction happening. How long does it take to finish? You could also apply that to a liquid pouring. You have different rates of liquid pouring, right? Or a fluid transferring or whatever. So rate always has to do with, and in a general sense, change over time. Is that what rate is?
Yeah.
It's how much something is changing over time. Rate times time is distance.
Oh.
Yeah. So yeah, the idea of something happening over time. That's what we're going to be doing in this chapter. So there's two different ways that we can, if we have a chemical equation, in this chapter you're going to see this frequently where I'll just give you a generic kind of symbol for a reaction. A yields B, for instance, or A yields products, the word products. So sometimes I give you a specific reaction with the equations, and sometimes it's just going to be generic, like in this case. Now, we could measure the rate, whichever one was easier for us to do. We would either measure how fast this is getting used up or how fast the product is being made. Maybe the reactant is colored, and we could monitor how fast the reaction is losing color. Maybe the B is a precipitate, and we can measure how fast B is being made, how the weight of the precipitate is changing, something like that. So either way works. You can measure the rate of the reaction with either one. The graphs would look different because A, the concentration starts high and then goes down. B, you start with none and then it goes up. Thanks for coming. Did you try to hide out and stay for B lunch and they caught you?
We went and dropped a water bottle off the front. We left it at lunch.
It was like 6 minutes.
It's a
I'm
long
only
walk.
yanking your chain. I'm only kidding. Would the slope of the change of A be the same as, with the opposite sign as the slope of the change of B?
Yeah.
Yeah.
As long as, what?
The equilibrium.
Not equilibrium.
There's nothing lost in the process.
Okay, as long as there's nothing lost, yeah, because you gotta be 100% efficient. Something else though too. Not just balanced, but they need to have the same coefficient ratio. What if it's 1A yields 2B? Then wouldn't B be twice the slope of A? Yeah, so we do, as long as they have the same mole ratio, then they'll be the exact same slope, but one will be opposite of the other one. So that's what I'm saying with this. The rate, if we were using A to monitor the rate with, it would be, because the rate has to be positive. So the slope of change of age over change in time would be negative. So we have to put the negative sign out in front of that to make it positive. Then the slope is positive right off the bat here, so I don't have the negative sign in front of that. David?
Wait, yeah.
No. The fact that there's two reactants? No, if whichever A or B is easier to monitor, like I say, if one of them has color and the color's going away, or if it's a gas and you can monitor the pressure of the gas, that kind of thing. Like if we wanted to monitor the rate of iron rusting, you could monitor the pressure of the oxygen. And then you got the iron, which it's hard to monitor a change in the iron because it's going to have rust building up on it. So you might want to watch the pressure of the oxygen. But that still would have, now the iron and the oxygen, if they don't have the same coefficient ratio, they're not going to have the same slope. But as long as you know one of the things, reactants or products, then you know what the rate is. Yeah.
Isn't how reactants are the same coefficient?
To have the same slope. Okay. All right. So that's what I have on this slide is this bit about the coefficient ratio. As long as you know the rate of any of them, you can always find the rate of the rest of them. Remember that the reactants are always going to have a negative change because they're going down. The products always have a positive change because they're going up.
Having a seizure. They erased it.
The whole or did it move to someplace else?
This is the same.
Got erased. Sorry, Emily.
That's not how you measure. This is
Yes, ma'am.
Is relative rate a vocab?
No, I don't think so. The word relative just means compared with other things.
Okay.
So what I'm saying here, as A goes down, if it's a 1-to-1 ratio between A and B, B is going to go up at the same rate, assuming 100% efficiency again. But C goes up twice as fast as A goes down. And so relative just means compared to others. Are we all good with that? Now, starting on the next slide, just be warned that it may take another day to fully grasp this business about order of reaction and rate law. if at the end of the hour you feel like, oh man, I don't know what even it just happened, don't fret. You'll, I think, find this to be a pretty easy concept tomorrow. But today, especially with me going through and showing you how we come up with these equations, it may cause you to kind of get lost. I don't like, though, just giving you the equation, not telling you where it came from. So I feel obligated to do that, and just know that it may kind of leave you with a sense of, I don't really think I followed all that, and that's fine. It's not a big deal. Tomorrow, it will all come together, and it actually turns out, I think rate law is pretty easy, but you just have to practice and kind of get the feel for it. Starting from nothing, it may take a little bit. So, again, we're going to be looking at rate law. There's two different kinds of rate law. They compare the concentration of the reactant to either the amount of time it takes or what the rate of the reaction is. Both types of rate law are from calculus. One is called the differential rate law. The other one is called the integrated rate law. You have to take a derivative to get this, take an integral to get this. I'm going to show you that, but you're not responsible at all for doing any integrals. There's not one time you're going to have to do it, except for watching as we go through this, derive it. So differential rate law compares the rate of the reaction to the concentration of the reactants. Then the integrated rate law compares the concentration of the reactants to time. So here's a couple things about rate laws. First, your differential rate law is going to look different. They're both just mathematical equations, but they look different. They look very different. But they say the same thing. And the next bullet point is very important, and we have to keep this in mind all the time because this is a real hang-up very often for people. Both types of rate law, they have to be determined by experiment. You can't just look at a chemical equation and say anything about the rate of a reaction. You've got to run it and make experimental measurements of concentration, time, or concentration and rate in order to determine a rate law. Now, if you take, I've written a couple of chemical equations up here. If we compare the first to the second reaction, the first one is A yields Y, and the second one is 2B yields Z. When you look at these two chemical equations, you can't tell at all which one is faster. Just because this has only one A does not make that slower than the one with 2B. There's a lot that goes into what causes a reaction to go fast and what causes one to go slow. So you're not going to ever look at an equation, including this, we don't look at this and say, oh, because there's 2 reactants here, that must